This webinar is brought to you by Engage, an NSF project, and is co-sponsored by the ASME organization. Our topic today is Engage's Everyday Engineering Examples, adding relevance and interest to engineering classrooms. So let's get started. Our speakers today are Pat Campbell, who's a co-principal investigator of the Engage project and is also president of Campbell Associates. Our co-sponsor is Tom Perry, Director of Education at ASME. And our featured speaker today is Tonya Nilsson from Santa Clara University. And now I just want to turn it over to our first speaker, Pat Campbell.
Thank you, Jane, and welcome everyone. Before we get started, what I'd like to do is tell you a little bit about WEPAN. WEPAN is one of the co-sponsors of the webinar and also a part of our Engage project. WEPAN stands for Women in Engineering Proactive Network. And as you can tell from the slide, it's got a wonderful set of values of knowledge, collaboration, inclusion, and leadership. The core purpose of WEPAN is to propel higher education to increase the number and advance the prominence of diverse communities of women in engineering. Currently, WEPAN has 700 members, including me, from 200 engineering schools, corporations, governments, and nonprofits. So we urge you to learn more about WEPAN. You can find it at www.wepan.org and think about becoming a member, or heck, even making a donation. So we were very delighted with the response we got to the webinar, and we have over 300 registered participants from all the way around the world. And all I have to say about that is thank you very much, ASME. We're delighted to have you all here. We particularly wanted to say thank you to the mechanical engineers who are on. So we know how many are on, but we don't know much about who you are. So what we'd like to do is do a short poll. Who is participating in the webinar today? Okay, so what we're finding is that most of the folks here are faculty members. Wow, almost 3/4 of the folks are faculty members. And we have a couple of administrators, a bunch of others, and a couple of graduate students. And welcome to you all, especially your graduate students, because we're looking forward to you being faculty in the future. So now that we know who's on, what I'd like to do is to take a minute to introduce you to Tom Perry. Tom is the Director of Education at ASME, and he's just a fabulous person, even when he's not recruiting all kinds of mechanical engineers to join our webinar. So over to you, Tom.
Oh, thanks, Pat.
You're welcome.
I will tell you that that photograph is a little bit misleading, and that I'm a lot grayer now than I used to be. What I want to say is congratulations to Tonya for her work and the Engage folks for putting this on. I'm going to set a little bit of a stage on the back end of an engineering education in the next three slides. Because what we're going to be talking about in the next hour really has to do with what happens in getting to that back-end stage. And our strategy in ASME education is increasingly being informed by what's been referred to as our Vision 2030 project. And some of the data results are in the next two slides, and I will show you something that we just recently discovered and we'll be inquiring on the third slide. The most important thing here that struck our attention was we could have potentially predicted what some of these responses would be from supervisors of entry-level engineers. These were people who hired and directly supervised, not really far up the management chain as far as supervision goes. And fundamentally, when our approach attitude has been, if 25% of engineering managers in industry say we have a problem with the graduates that come in the door, we're not that worried about that, frankly, because when push comes to shove, the university is not your training department. So you have a 25% have an issue of this or that, okay, go ahead and take care of it. When that number gets to be 35, 45, 55%, then we think we still have systemic issues that we need to tackle. That practical experience and how devices are made to work as 1,400 engineering managers say we have an issue here, we have to pay attention to that. The communication skills, as you've seen, and so on. But related to this particular webinar is that practical application, practical experience. On the next slide, we get this similar response, although there's a bit more confidence on the part of the young engineers who are working. And we asked about 1,200 of them about how they currently assess their readiness for engineering practice when they came aboard and had been working over the last couple of years. And the number one, as you might expect, is industry codes and standards and that sort of thing, because that's not a big part of the engineering curriculum origin. But the still as a number two item, that 37% of those 1,200 on the practical experience. How do I get that? I wish I had more of it. I didn't feel like I had enough of it. Now, relevancy is the key in all of this. Practical experience, I would submit, turns knowledge into competency, and that's an important changeover in the course of an engineering education. But first, you got to have the relevancy part. And there's another major initiative and major thing that ASME is paying attention to. That's depicted on the next slide, which for years we've been looking at the number of women in mechanical engineering in a little bit the wrong way. And when we started looking at the data a little bit differently and began to look at the women themselves as opposed to as a percentage of males, which hasn't changed very much in a decade, but the number of males has gone up tremendously. So therefore, the number of women has gone up tremendously. And we discovered we've got almost a 40% increase in the number of women studying ME in the last 5 years. We're about to embark on a study to ask those nearly 1,300 women why that is, what they hope to get out of it, what works and what doesn't work, specifically for mechanical engineering. The gender studies in mechanical and engineering and versus other disciplines have been around for a long time, but there's nothing out there that is specific to mechanical, and we're going to work that. Relevancy, value is exceedingly important from the research that we've seen on gender differences in women. And I'm going to leave that right there because that is really where we're headed, increasing the relevancy of the engineering curriculum and in the hopes in the end turning some of that knowledge that is in there into competency. Thanks a lot, Pat.
Thanks, Tom. It's actually learning about the almost 40% increase in the number of women in the last 5 years is quite awesome. And I'm looking forward to finding out about the results of the study that you're doing, and hopefully we'll even have another webinar. So this ties very well into what ENGAGE is and who we are and why we're here. As Jane said earlier, ENGAGE is a project that's funded by the National Science Foundation. We have as our goals to increase the capacity of engineering schools to retain undergraduate students, particularly in the first and second years, by facilitating the implementation of 3 research-based strategies. They are to improve and increase interaction between faculty and students, and we'll talk a little bit more about that later. To improve spatial visualization skills of students with weak skills. And what we're going to be talking about today is to use everyday examples in engineering to teach technical concepts. Now, all of these 3 areas improve student retention in general, but they have a particularly positive effect on the retention of women students. So who's in ENGAGE? Well, at this point, we have 20 schools that are using everyday examples through ENGAGE, although there are many other schools that are using it not officially through ENGAGE. We will be getting more schools involved, and indeed we have a mini grant opportunity for $2,000 that we'll tell you about later in the webinar in case your school would like to be involved. So that's a lot of background information. Let's get going and really get into what everyday examples are. And that's what we're going to do next. But before we do that, let me introduce Tonya Nilsson. So Tonya's going to talk about E3, the everyday examples, what they are, how they work, and ways that they can be used. But let me introduce Tonya to you and give you a little bit of her background. Tonya is a lecturer in engineering at Santa Clara University. She was previously a tenured associate professor at Cal State Chico. Tonya is an advocate for excellence in engineering education. She's worked extensively with ASCE's Exceed teaching workshops and the National ASCE Committee on Faculty Development. Tonya earned her BS in architectural engineering at Cal Poly, St. Louis Obispo, her MS in structural engineering from Stanford, and her PhD in structural mechanics from UC Davis. Yes, indeed, she is a California woman. So over to you, Tonya.
Thank you, Pat. That still is just such an uncomfortable thing to have someone announcing you. Hi, everybody. I'm so excited to be here. And the first thing I just want to do is make sure that we're all on the same page of what do we mean by an everyday engineering example. And as we can see on the next slide, we have some pictures of everyday engineering examples. And they're really, I used to go in the classroom, I teach a lot of mechanics, materials, strength of materials, and I'd want to talk about bolts shearing, and I would show pictures of beams and columns connected, or where a shock absorber comes down in a car, and say, right, you get this. And the poor students were so shocked trying to figure out what they were looking at that it was meaningless to them, versus using the bicycle. They've all attached to their front wheel or taken it off at some time, or they're looked at how their pedals are attached, or at least aren't intimidated by that because it's familiar to them. So these everyday engineering examples are using things that the students are already familiar with or comfortable with, so that they can visualize the uncomfortable or new theory you're talking about. And so it's pretty useful because they really tend to relate to it a little bit more. And we definitely want to know, first off, in our audience, who might be using everyday examples. So we have another poll. So if you could take this poll and tell us, are you using them at this time? Do you plan to? You're thinking about it? Or just straight up no?
I like, Tonya, that you started by explaining what everyday examples are, because I think it's really important that when we're talking about everyday examples, we're talking about examples that are everyday to students, not necessarily to those of us who may be significantly older than the students. Our everyday and their everyday may be a little different.
Yeah, and definitely many years in the classroom, I've learned that the hard way. Look at me. I have no idea what I'm talking about, even though it seems very general to me. So
let's see what we have.
Yeah.
So we have about 2/3 actually use some everyday examples in the classes. A couple plan to, and another couple of thinking about it, and very few don't and just don't even want to think about it, which is great. So Tonya, could you tell us a little bit about why everyday examples are so important?
Yeah, I would like to, because to me it sort of justifies why would you even take any extra effort, which I have to say, though, the E3s and the Engage program make it very little effort. But some of you may be familiar with Richard Felder. He is in chemical engineering in North Carolina, a professor, and he has developed learning styles with additional colleagues and has done a learning style assessment that you can have your students take online, which I do often. And he actually has 5 categories. This plot shows 4, but are students active learners or reflective learners? So do they like to experiment hands-on, get into example problems, or do they want to sit and reflect? Are they sequential, learning in linear steps, global, I need to see everything and then it all comes together? Sensory, these real-world experiences, which E3 is great, versus intuitive. And then, of course, verbal, which is written or spoken word, versus visual. There's one more category that I'll bring up in just a moment, but I do survey my students, and on the next slide I actually have the results of a typical sample of my students. This was taken this quarter, and 88% were visual over verbal, 58% active to reflective, so that's pretty close, though 2/3 almost were sensory, and significantly more students were sequential. So how does this compare to how we teach? And what we see, and the studies that they found, are that most students are visual, sensing, active, and sequential, which is exactly what I found. They also find they're inductive, and inductive means you want to learn by experiencing things, developing your theory through personal experience, which is sort of how children learn. You touch something, oh, the stove is hot, versus deductive, well, you learn the theory first, and then you see how it applies to real world. Unfortunately, that's very hard to test with a multiple choice sort of online assessment, so that's not included in Felder's online assessment. But the problem is most teaching is verbal, It's intuitive, not sensing. It's neither active nor reflective. It is sequential, but then it's also deductive. We put the theory up first and then sort of give examples. And so there's a big mismatch between how we teach and how most of our students prefer to learn. And so what I prefer to do is add the E3s because they allow us to teach to all the learning styles. And regular lecturing we see already addresses those students who are verbal, intuitive, sequential, and deductive. We don't want to leave them out, but just including some E3s can bring in both active and reflective activities, hit our sensory, our visual, and our inductive learners. So we get 9 out of the 10, which is really exciting to me.
Tonya, that really is exciting because I think the idea of different students have different strengths and different better ways of learning, that if as faculty we can use multiple modes of instruction, we've got a much better chance of reaching the students.
Agreed, agreed. So so what is an E3, right? So let's try to get an example of what this looks like. So I taught, I've been teaching mechanics for over a decade. And axial stress, you'd start with a bar, you'd say you'd load it, you'd get your axial stress formula P over A, the deformation PL over AE, but then we'd start looking, okay, how can we use deformation and kinematics to solve statically indeterminate problems? And we'd start looking at, some of you I hope in the background are laughing because you've seen the copper pipe with the aluminum center, and we use this with our students as a statically indeterminate problem. And I have to admit, maybe there's something in mechanical. I am a civil, but I have no idea what the real-world application is of a copper pipe with an aluminum center. So, the students ask me, like, I don't know. It's just an example. But instead, I know it's awful. Instead, what we can do is there's a great E3 that's been developed and available to the Engage program is using your iPod and your iPod cable or an iPhone. The iPod cable is a copper wire core with the shrink tubing on the outside, and it's a composite. So you come into class, it's really fun. I come in and I'm wearing a headphone and I'm rocking out in the front of class and I'm not talking to the students and they think this is really weird. And then I turn it off and I start class by asking, has anyone ever broken their headphones, or has anyone ever dropped their iPod and had the headphones catch it? Well, what kind of force does it take? And then I actually have, I've cut up some wires so you can easily get shrink tubing. I have shrink tubing without wire in it. I have wire without shrink tubing around it. And then I have wire with both. And I pass it around and I let the students pull on it and let them sort of explore what happens. And the shrink tube really stretches. The copper wire doesn't, but when the two of them are to composite together, it doesn't stretch either. Anyway, they can really noticeably tell. So we talk about, well, which takes which force. We look at that it's a composite, and we go through then how to solve that problem. And they've experienced that the two have to deform the same amount when it's a composite. And the students love this. They get it. It's why they understand this material. And then you can, take them to another level and give them another composite like bones for biomechanical students, or you can move into other topics, concrete with rebar in it for civils, however you're working.
And I love the idea of the legs of the elephant versus the legs of the mice.
Yeah.
That's a nice visual representation.
Yeah. But it's not just here. Bending, if anyone's ever taught shear and moment diagrams, students don't really understand what is it representing. And they may not have really thought about beams, but I tell you what, at least on my campus, I can't go a day without dodging a skateboarder, and it's pretty rare, unless it's raining, that there's not 2 or 3 skateboards leaned against the wall in my classroom. So I typically would not come to class riding a skateboard. I've tried that. It wasn't pretty. So I ask a student to ride their skateboard across the classroom, or before class I'll have a fun YouTube video with music and crazy tricks happening. But then we talk about, has anyone ever broken a skateboard? And usually someone has, or seen one broken, and then, well, why? What were the forces? So then we can draw the shear and moment diagram for the skateboard, and then we say, well, what if the border moves? And draw another one, and also then talk about, well, what was the max shear and what was the max bending? that developed, or the max bending moment, that developed due to different loading configurations. Someone's sitting, someone's standing, and they start to see a little bit more real application of it. And then they start asking crazy questions. Well, still, why did it break? And at least for me, I review shared moment diagrams in my class, and then the next day we go into bending stress. So I can go right to an example that is then the bending stress of the skateboard, and we can analyze that. And it just leads us to discussions about different things that could be beyond the scope of the class, but at least they're exciting and engaged, which is fantastic.
I love that the idea, and somehow with a project named Engaged, it's probably not surprising that we're all very excited about the idea that students are engaged, but engaged students are listening students, are students who are motivated, and that's got to be good for learning. Now, Tonya's been talking a lot about everyday examples. How about we see one in action? And this is by Ian Patterson, who is one of our E3 gurus, a mechanical engineer that you'll find out a little bit more about later, and all the different kinds of work that he's been doing. I love this example on free and forced vibrations because it's so easy. And we're hoping it'll show. Now, as you can tell, you can see it, but you can't hear it. Tonya, did you want to talk a little bit about what Ian's doing with it?
Sure, absolutely. So right now he's trying to talk about free and forced vibration. So he's just flinging, holding the ruler down and then sliding it back and forth. And you're hearing a different pitch in the ruler as the frequency is getting higher as you slide the ruler back. And then basically he talks about you can then relate the kinetic and strain energy in the ruler to find the natural frequency of the ruler. And then to verify that the students actually understand what they've done, have them repeat the analysis with a different example. And he suggested using an antenna with a ball on the end. And then they can check their understanding. And it's just that simple, easy demo.
And part of the things I like is having a ruler. Pretty much everyone has rulers around, so it isn't a whole lot of work, and it is something that students can actually do themselves, which is pretty exciting.
Yeah, now, and they make a lot of noise, and they're totally engaged. I mean, I guarantee you they're engaged because they want to see what kind of noise they can make with their ruler.
I like that as well. So we've been talking a lot about everyday examples. I'm an educational researcher, although I started in math and physics, so I'm always interested in, so do they work? What kind of impact do they have? So actually, yes, everyday examples in engineering do work. Students who are involved with everyday examples retain information better and continue on with a course of study as long as it involves the subjects and activities that interest them. And this has been done with engineering students as well as other students. Basically, using everyday examples is helping students learn. And Tonya, I think you have some data on that.
I do, actually. So I got really excited when I learned about the E3s, and I learned about them in spring of 2011. So I had two cohorts of students, mechanical engineering students, both winter and spring of 2011, who did not experience the E3s, the skateboard, or the iPod cable demo. So the following winter 2012, they take a machine design course that requires them to just use their strength and materials over and over again. So the instructor there let me give them a pop quiz day one that had some different questions on it, including moment diagrams and axially loaded composite or statically indeterminate members. Their retention on the question was very multiple choice. It was 46% for moment diagrams, 71% for the axially loaded. The following winter and spring 2012, I taught that material with the E3s, and in 2013 gave the same pop quiz day one, so they haven't reviewed this material in a while. The moment diagram retention, or correct answering, went up 61% to 61%, not by, excuse me, but up to. And then for the axially loaded composite member, the iPod cable demo, went up to 85%, just based on using the E3s.
That's amazing, and I think it's particularly important because what you were doing was you were testing for long-term knowledge, not the, all right, can you cram it in the day before the exam? And the idea that E3 learning sticks, I think, is really important. We did have a comment from someone who was asking where one can get the videos. The videos are available in the engageengineering.org website. Just go to the Everyday Example Resources section, and there are a whole lot of videos that, that you'll be able to download. So, Tonya, you found that using everyday examples improves student longer-term knowledge. There have been other studies that have reflected on that too, that what we found is that when you're teaching concepts with familiar examples, like exploding hot dogs, for example, iPods, as we've already talked about, and bicycles, that students are more interested and the students learn better than when the more traditional examples like I-beams and cylinders are used. Now, one thing that we have learned, and it's important, is that if you just use one everyday example, you will get students more interested. You're not going to have a huge impact on their learning in general. In order to do that, you really need to kind of infuse everyday examples kind of throughout the course. Indeed, we found that with folks who are using 6 or more of them, had an impact on students' overall grades. For those who used fewer, it had an impact on the concepts that were being covered by the everyday examples, but not on overall grades as a whole. So everyday examples have an impact on students, but also have an impact on instructors. The instructors who were using everyday examples in their classes, they actually got significantly higher student ratings than they did when they taught the same course without everyday examples. And they also said that it kind of made a difference on how they taught as well. As one person said, it changed my teaching because I had to be more responsive to students being incredibly creative. Another person said, because of using everyday examples, I had to talk more about how to manage projects, not just to talk about numbers. So everyday examples can make a difference in lots of different ways. Now, there is a little brief on everyday examples. You can see it in the little small print on the bottom that you can download from the website. But then also, if you have strong masochistic tendencies and you would like all 9 yards about the effect of context on student engagement in learning, aka everyday examples, that, I was going to say last year, but it's now a year and a half ago, Ian Patterson, whom I mentioned before, and myself and Eileen Bush-Vishniak and Daryl Gilliam did a research study on it that's available at the European Journal of Engineering Education. And now I had said that if you covered something with an everyday example, that students did better on that concept. And guess what? Tonya has some data on that.
I've been the data queen the last year and a half. So what I did is, because I do teach the same course a lot, I have some numbers just on using a composite, statically indeterminate, axially loaded member from an exam question, and there's multiple sections in here, but the average of students who learned it without E3s was around 55%, 54%. Once I started teaching with E3s, that average actually jumped up to almost 80%, and that's in multiple sections that are taught with the E3s. So it's pretty exciting that their performance jumped so much. I don't have on here the numbers for using the moment diagram, how they did on moment diagrams using a skateboard, simply because the students actually, the way I was teaching moment diagrams, they were getting it pretty well. So they were already around 80%, and so including the skateboard demo, by the time we got to the exam, they had figured it out, and so including the skateboard demo didn't really up. So I didn't see a big jump, which tells me if I only have time for one of these to include them in my class, include it where the students are weakest. But I would still continue doing the skateboard demo simply because I now see that how it improved their long-term retention of the material, which is critical really in the long run.
That's a really good point. Oh, go ahead, Tonya, I'm sorry.
No, go ahead.
But I think your point about you introduce things step by step, and the idea that everyday examples are motivating is across the board, but to kind of prioritize so that you start with the everyday examples for those concepts that students are having difficulty with sounds like a really important way to start. Then as that grows and you get more experience with doing it, putting it in more and more, it makes good sense.
Yeah. And, you know, it's interesting because I've been doing a lot of active stuff in my classroom. I've tried to create my own demos before I learned about the Engage program in E3s, and I have spent a lot of time and effort trying to come up with things. And then I discovered E3, and they're already done. There's a whole pool, literally a lesson plan. If you're even slightly considering this, just decide to consider it, because it is the easiest thing. You literally have a lesson plan already set up that you can find out on the E3 website, which Pat will be showing you in a little bit, that here's the demo, here's questions to ask, here's example problems. It's done. And I have found that the E3s I found here are more effective than the ones I made up myself and spent all the time on, which is just, ugh. But some other ones that we have to show you, because we have a couple more just to show you, is, you know, even for freshman engineering graphics, bring in a cereal box. Have them, deconstruct the box where they can, first estimate volume and surface area. They can disassemble the box, measure everything, see how the patterns all go together. And it's a great tool to use for pattern development. And we all have these. We also have one of a really fun one is fluids and bubbles. So if you want to talk about the properties of fluids, just bring in some detergent and a straw and have the students blow bubbles, and then you can talk about the surface tension and how the fluid behaves like a tensioned membrane. So these are easy examples to bring in that don't take a lot of effort on our part as faculty.
Well, and also, Tonya, that the bubbles is part of 12 different activities in fluid mechanics, everyday examples that you can see a copy of the book right there on the slide. And we're pleased to say that everyone who's on today's webinar will receive links to download this set of activities, but also some of the other activities that Tonya's going to talk about.
Well, the next one is one of my favorites. I actually did use this before. I found it on E3, but one of the links that it's going to be available in the real-life examples of mechanics of solids, that you can see that book down in the bottom corner. It's great. The buckling of the railroad occurred when there was a heat wave in London, and it derailed a Guinness train, which for some people I think is the end of the world. And so it's really fun to go to that link. The link is there. But what you're talking about is that thermal expansion, and if the member is not free to expand, if it hits a wall, not only do you have a statically indeterminate problem, but that you'll actually have stress develop in the member and how much stress will develop. And so you can, just talk about what would the thermal expansion be. This example gives you dimensions for a typical rail line, and then talk about, well, what if it's allowed to expand 4 millimeters, but then is stopped from expanding, and what kind of stress is developed. So there's a great example that goes in, and they know things will expand, but these pictures are very dramatic to them. And I just show the pictures in class, so it's very little effort on my part as far as a demo.
And also I see too that in a lot of the everyday examples there are links to either YouTube or in this particular case BBC, so that if you want to have the video, the information about how to get the video is right there. You just need to click on it. So that's nice. Now the next one, Tonya, that you're going to describe, I think is one of my favorites. And yes, this is also another set of real-life examples, this one in dynamics, that you'll have the link to as well. But why don't you talk about paper airplanes?
All right. Yeah, I kind of like this one too. And it is just talking about kinematics, the movement of a particle. And so it's kind of fun. You can ask the students here, the activity is to, write on a sheet of paper 3 reasons why they chose to study engineering. So it's kind of fun. You can tie that in and get them engaged just so that they have to put something down personal, but then they have to throw it to someone on the side of the room. And it's crazy the shapes you'll get back out. Some students will make airplanes. You may or may not have anybody try to toss the sheet flat, but you can do that and really show the difference between what you get based on the shape and what you would get for the movement. And then you can discuss that really only the balls of paper could be considered something as a particle with mass, with negligible size and shape. So they can really see the difference in how they behave, and they're all familiar with throwing paper balls or throwing airplanes. And again, there's a whole book from Ian Patterson on real-life examples in dynamics of engage activities.
And also, we did get a comment asking if everyday examples had examples in other engineering fields like computers and electronics. And yes, actually, I think it's 18 different fields that we have some everyday examples, and we're adding new ones always. So we will get into that a little later in the webinar. But yeah, since this was sponsored by ASME, we were doing a little bit of a mechanical engineering focus. Now, we've talked a lot about, well, lots of things about the everyday examples. We've talked about the impact on learning, the impact on motivation. But there's another area that we haven't talked about that really is kind of important. And that's faculty-student interaction. That, as I said quite a while ago, that improving faculty-student interaction is one of Engage's strategies. And as faculty become more approachable to students and they get more involved with students academically, it has a wonderful impact on student retention and on student achievement. And one of the things E3s helps to do is to make faculty more approachable. Nothing like having your faculty member come in on a skateboard and fall off to make a faculty member seem approachable. There's been a lot of research on the impact of faculty approachability, of faculty mentoring. And certainly engineering students report that faculty mentors play a pivotal role in supporting students as they go through the engineering curriculum. When you have a faculty mentor as an engineering student, you're much more apt to continue. Your satisfaction and your route to degree is linked to the kind of interactions that you have with faculty. And all this makes a big difference, so that there are a lot of tips about things you can do, calling people by name, even smiling at people when you walk down the hall and see them. But using everyday examples, using the kind of things that tie you and the students closer together really makes a difference. So we've been talking a lot, and would like to get a little feedback from you. That you're here learning about everyday examples, and what we're curious about is, what do you see as major barriers to instructors implementing everyday examples in their classes? Yes, for yourself, but perhaps for others as well.
And while the poll's going on, there was a couple questions that I could answer really quickly, and one was just the sample size on the exam problems. And the students who performed poorly, that was pre-E3, there were 2 sections over 2 quarters, and that was, I think, about 61 students. And then the following term I had much larger sections, and it's over 121. So I actually used the E3 in classes that almost had 50 students in them, as opposed to where I was teaching only 30, where we say usually students do better, and they actually did better because of the E3s. And the other question was balancing the complexity of real-world examples with understanding the concepts. And so many of these E3s are actually pretty, you can bring them down to a really great starting point, and when they get that basic understanding, you can actually take them to more complicated problems and move them along. So number the lessons when you do go out and look at these E3s, that they start you small and build you. So they're a great tool.
And I think earlier on you were using what we call 5 E's example, where, and a lot of the lesson plans have that, where you start with the engagement and exploration and explanation, but then you end up elaborating and getting more complex, and then involving students in the actual computation, so that coming in and doing something fun with a ruler is a start, and then from there you keep working and becoming more complex with it. So how about we see what people see as kind of more important barriers?
Making time.
Making time. Making time, getting materials, don't have any E3s, we can handle that. Unsure about student response, and then also, before we go on to some of the others, how about you tell us a little bit about using E3s in large classes?
Well, we thought this might came up, so we did put in a slide for this. I'm at a private university, so a large class here is 60 students, but I have taught in the UC system where I've had much larger. But one of the things I use is, I happen to be a Mac user, so I have a laptop camera and FaceTime. You can get the small little web cameras as well on a PC, and this works just fine. But I'll often, if the room is big, just whatever thing I want to show them, I just turn on my whatever will hook up to my camera, and I just put the demo right in front of the computer, and I project it up on the screen so that they can see it. I'll have multiples also that I'll pass around the class. When I do the iPod demo, I did that in a room with 50 students, and I knew how many rows there were in my room and how many seats per row. So ahead of time, I just got little Ziploc baggies, and I had one of each kind of wire in the Ziploc bags, enough for each row, and I just, when I wanted to hand them out, all I had to do was walk down the rows and give each row a pack of each one, and I told the students, you in the bag, you're the keeper of the bag. When I say, pass each bag up, everyone keep these sorted in the bags, and at the end of class, I told them to pass them up, and I got back my perfect bag, so I'm ready to go for the next term. They'll work. They're great. They were excited to have them. They're going to help me out.
That's great. Now, we had several people gave the feedback of saying, why do we have to pick one? There could be more than one barrier. Not to worry, folks.
Oh,
we're going to go over all of them. Now, one of the things that was the most picked was that thing about making time. Do you want to talk a little bit about somehow getting the time to do this?
Well, I think that's actually, if you are considering anything to engage your students, I truly believe that these E3s then are your ticket, because as I mentioned, I've spent a lot of time looking for and trying to come up with my own demos and developing the demos, building things in the shop at home, whatever. When I then went out to the E3 website and thought, oh my God, it's all here for me. Done. There are lesson plans out there that literally do step you through a whole lesson, right down to homework assignments that go with the topic, that do move you all the way from that initial engage and let them explore with it a little bit to start relating the concepts, all the way to elaboration and really further reinforcing the fundamentals of their education. And it's just there. So if you have the time to just go out to the E3 website, look up your class, look up the topic, and print it out, you're kind of done. It is 15 minutes. It's insane. And even if there's not a full lesson, for a lot of them there's at least ideas of what the demo are that you could tie in and already use then the example problem you use on the board, but you can just relate it back to the demo, the suggested demo that's out there. It's so much easier.
You raise a lot of good points too, and also, I mean, some people were concerned about getting materials, and some things can be very complex. Actually, on the exploding hot dogs, Ian actually brought in sausages and a hot plate and actually had the sausage casings explode. But I had another faculty member who just showed a picture of the sausages exploding, and that was enough to increase student understanding. So that if you're worried about getting materials, then start with things that are easy. Start with things like bubbles or paper airplanes or things that it really isn't much work to do. And Tonya, is there anything that you wanted to say about, some folks were unsure about what the student response to this would be?
Sure. The students really, really like it. The fact that they get to be engaged, I've had students come up after class and tell me, oh my gosh, this was great, this was fantastic. I actually surveyed my students then to class to ask them, how was your interest level in the class? And I did this pre and post E3s, and their interest level in the class actually on a Likert scale of 1 to 5, 5 being I'm so interested, and these are sophomores, they went from a 2.54 to a 2.94, so that was a big jump. They told me, I did another survey, how did this demo help you understand the material? And the iPod demo on a scale of 1 to 5, 5 being it's why I learned the material, period. The iPod demo got a 4.18, and that's out of over 100 students said that. So they love it, and I've messed up. I've had stuff not work that when I tried to think of them on my own, but they get that you're trying, and they're okay with that. And if you throw out a demo that's you think is everyday and they don't, just ask them. They'll tell you. And try something new the next time.
And also, I mean, we're always embarrassed when we try something and it fails. But often, pedagogically, when you try something and it fails, it's a better learning experience for the students than when you try it and it succeeds.
Yeah,
so,
it's still better than lecturing.
So in response to the, and as you can see from the slide, in response to the questions about I don't have any everyday examples, oh, trust me, you do now. So we'll go through this a little, but we're always interested and excited about getting new ideas and new everyday examples. In fact, we got a comment that just said this webinar has me, this faculty member who's been working on multiple loads and elongation as a topic, and the webinar has me think about the opening scene of Les Miserables when the convicts are pulling in the ship as an example of stretch from multiple loads. Fabulous. That the idea that as you think more about everyday examples, you start generating ideas on your own, and that really gets everybody excited. So, as you can see, we have the website. You can see it is engageengineering.org. And this is just a list of some of the activities, some of the areas in which we have activities. Ranges from calculus and differential equations all the way down to thermodynamics, properties of materials, physics. We need more. We particularly need more from electrical engineering. So if any electrical engineering folks are here, contact me and let us see what we can do. So let's go in and look at a little bit. How about we take a look at fluids? So if you clicked on fluids, then what you have here is the different lesson plans that we have for fluids. And in this particular case, if you go a step further, and then you get into one of my favorites, which is water guns and super soakers. That's because I have a 10-year-old grandson, and he's heavily into super soakers. And water guns and super soakers are not just fun, but they're also a nice way of looking at pressure as stored energy. This one, I'm happy to say, was developed by David Benson, who is one of the engaged team members. And so this is, we don't have a standard format, but this one really kind of gives kind of the amount of information that you might need for this to get started, what the objectives are, the purpose, equipment, and then if you go further down, there will be the step-by-step things you can do for the activity, and then the formulas and things like that. We've been talking a lot, and we've been getting some questions from you, which has been really great. But let's take a minute and do some questions and comments and ideas. One of the questions that's come up is, how do I know if what I think is relevant and engaging for students actually is?
It's probably not.
Ouch.
Ask the students. Definitely ask the students. And that's why I said I've gone in and failed, because I thought something was cool. So, you know, I got to get over it. I'm way older than they are. A lot of times I'll ask them, you know, does anybody know about this? And they'll laugh at me and tell me no, and I'll say okay. And then, but the nice thing is a lot of times I'll sit down with my juniors that have then had the class, who have now had a chance to think about it, and start asking them, and they'll come up with ideas for me, which is really great.
Good question. Do the examples work as well with female students as male students?
Really do. And in fact, a student was just outside my office yesterday lamenting about how her professor was saying, so yeah, when you lift the hood of your car and looking at the engine, and she said, I don't ever do that. I don't know what's under the hood of my car. And it was great, her look on her face, where these, it does work, because they can get active, they can get engaged, especially if they have a demo they can look at or touch. So yeah, as long as it's every day and you don't go back to those sort of standby, the car, the machine, the gears that they may not have played with as children.
That's a good point, and sadly, increasing numbers of male and female students haven't looked under their car or played with gears. As someone who used to be part of a race team when I was a faculty member, that makes me very sad, but it really is, and I think that ties back to what Tom was saying earlier about the dearth of real-life examples and practice tinkering and things, so that moving that forward sounds like a really good step. Let me ask another question, and this is a tough one. This one says, I use and bring a lot of real-life components to my class, and the students seem to like and understand the concepts discussed. But when you test them on an exam, their performance is, quote, back to normal, like not so good. So is their understanding different than their ability to perform on exams if we test them using the conventional tests?
That is a tough one, and it might be beyond the scope of this webinar, because there could be a lot of things happening. You know, what are your objectives when you're teaching them in their homework versus then at what level are you testing them? You know, so are they getting opportunities in the homework to work at the level that you expect them to then test on the test? And without knowing that, that would be hard to answer. I have found myself that when I use these demonstrations to demonstrate the exact same idea, they do tend to perform better, but I do have to follow it up with what sort of assignments am I giving them, what are my expectations, what are my levels of cognitive ability I'm expecting in the homework versus what am I then testing them at. And if they're in line, they do much better, but there could be other things happening.
Thank you, Tonya. That's, as you said, it's a really important question, and it's one that's probably beyond the topic of this webinar, but I think the idea of matching assessments to the type of learning is an important one. Okay, somebody had commented that some of the links are not live, and yes, those are the ones that are in the books that you will be getting the links to at the end of this webinar. So the activities for solids, fluids, dynamics, and thermodynamics, we will send you the links and you'll be able to download those. And we also have kind of a fun monthly everyday example e-newsletter with contests and things like that. And you'll get on that too. So you know what else you can do. Certainly find the videos and try some everyday examples in your classes. And this is my email address. I'm Pat. If there are ways that I can help you, if there are things that you would like to talk about everyday examples, if you have ideas for everyday examples, let me know. Also, I'm an assessment person, so if you want to talk more about assessment, let me know. So the final thing that you can do is apply for an everyday example mini grant. Now, folks have asked if the mini grants are limited to U.S. universities and colleges, and unfortunately they are. We're funded by the National Science Foundation, and we are limited then to within the U.S. or U.S. territories. Others have asked if they could apply for the grant even though most of their students are third year or they're teaching third year courses with sophomores in it. Sure. You will get the link in the email that will come out after the webinar, and what we're asking you to do in the application for the $2,000 mini grant, you attend an initial webinar discussion with the other recipients, integrate a minimum of 6 everyday examples, either from us or from others or from yourself, and at the end of the project, give a presentation to colleagues on the benefit of everyday examples while sharing strategies for how they might be able to do it. So you try out everyday examples, you come to a webinar, you do the everyday examples, and then you tell your colleagues about it. The deadline is February 22nd. We hope that you will all get involved in this and apply. And sadly, our hour is up. This has just been really fascinating. We hope that you found it useful. We'd just like to leave you with some pictures of everyday examples, including dog shaking, all kinds of things. So please use some everyday examples and stay in touch. We'll be in touch. And I just wanted to thank you, Tonya.
Thank you.
And thank you all for attending.